All right, so we are now in the last stretch of the course. We're up until this point, we've been focused on sort of backwards uh, facing concepts. We've been studying probabilities, we've been studying the important distributions, and we've studied the philosophy and practice of hypothesis testing. And now we're going to turn around and be user facing and be like, all right, when confronted with real life data that we get information from, how is it exactly that we go ahead and make sense of that? So we want to take everything we've learned up to this point, turn around and apply it to things that we might actually encounter. And you may think we've already done that in chapter 4. And really, what we're going to do in chapters 5 and 6 is very, very similar to what we've done in chapter 4. So, and the way we want to think about those things is completely unchanged. So I'm not going to go into a lot of details about that. But what I am going to do is talk some about uh, kind of a standard example I've been using in these videos, and from there we'll see. Uh, you may notice on the left that, or below me rather, it says that I've been lying to you this whole time, and there kind of sort of is a lie uh, that's crept in. So we're going to go ahead and represent the example, and this time let's see where we might spot the lie. So let's go ahead and start. Um, so as usual, a researcher weighs, let's say 40 purple microelephants, and then they have, I'm just going to go ahead and use the notation, average weight of 125 pounds, and the sample standard deviation is, the sample standard deviation is 20 pounds. And then we ask ourselves, let's go ahead and pose ourselves an H naught and an HA. So let's say the alternative hypothesis is that the actual weight of purple microelephants is, let's say, more than 110 pounds. And as the alternative or the null hypothesis, if we don't have enough evidence to show that, we say that it is possible that the average weight is only 110 pounds. All right, great. So far, so good. Let's drag this down a bit and let's go ahead and recap how we would have thought about this before. So what we are basically doing is here are all the purple microelephants in the road, so that's the population. And over here, from that, we get our sample. Right? So this is where our mean and our S live. In the population, that's where we have a mu and a sigma, right? And so what we said was, well, we have all these purple microelephants, and we're gonna reach in and grab out 40 of them, right? And when we do that, we don't know whether or not we're gonna get a bunch of really heavy elephants or a bunch of really light elephants. So this X bar is not necessarily equal to mu. In fact, it's very unlikely that X bar is mu, but it might be close, especially if n is big. And so what we said was, all right, we're going to go ahead and assume the null, and we'll assume that S is uh, uh, sigma, and from there, what we'll do is sketch ourselves a little normal curve where, because we've assumed the null, our 110 is there, we have a 125, our point estimator over here showing up, and then the standard error of this curve is 20, over square root of 40. And so we want to compute our p-value here by computing that area. And if that p-value is small, we can go ahead and assume that the 110 assumption was bad. And if the p-value is large, then we have to assume that the 110 assumption could be valid. All right. So where's the lie? I'm going to go ahead and pause for just a second here. And you can pause this video too if you want. Okay, so looking at all of these things, most of this makes sense, right? We know that the sample mean's probably not the population mean. So it's reasonable for us to assume that those things aren't going to be the same. And to actually test the likelihood of getting such a sample mean, it is reasonable for us to go ahead and then assume the null. Because if you assume the null and then everything works out reasonably, then the null definitely could be true. The whole point is that we assume the null and try to show that what we observed, this 125 pounds, is some ridiculous thing that can't happen, right? Equivalently, that the p-value is super small. And then the standard error of this distribution is going to be, it should be, right? What it should be is sigma over the square root of n, right? N is definitely 40. And then we're assuming that the sigma is close to the sample standard deviation, which is 20. All right, do you see where the lie is now? We know that when we reach into a sample and pull out a bunch 40 elephants, that the sample mean's probably not valid, right? And that's why right here we say, okay, these two things aren't equal to each other probably. But what lets us say that, right? If the sample mean's not valid, then why would the sample standard deviation be valid? It's certainly true, right, that we could have reached in and grabbed a bunch of elephants that are much more variable, right, than the overall population. We could have reached in and grabbed a bunch of elephants that are a lot less variable than the overall population, right? There's no reason to think that the sample standard deviation is accurate. So let's go ahead and blow this picture up. And let's draw a normal curve. Well, boom, there's our curve. This is with SE equal to, let's say, S over, or let's stick with the numbers, the numbers that we got. Oops. 20 over square root 40. Right? So we have that when we have this curve. But again, what we said was, hey, it's certainly possible that the elephants we got is actually more variable than the population. And if we were to sketch the population curve, they would be less variable. It's also possible that the elephants we got are less variable than the overall population. And I really wish these things would line up a little better, but we get the idea. Right? It's so your normal curve could be shifted in, it could be shifted out, right? The black curve is just the one version of the curve we get from assuming sigma is 20, but we don't know that sigma is 20. Sigma could be more than 20, less than 20, and we would get other curves. And so what you want to imagine here is that there is some sort of wiggle, right, that goes on here. And when we when we do our hypothesis testing, we have to account for the wiggle. Now, here's the good news. We know that when we are estimating, say, confidence intervals for the mean, say, and you're looking at say, a 99% confidence interval for the mean, right? The margin of error, let me go ahead and write that out. Just recall, the margin of error for the mean uh, is whatever z value you get for whatever confidence you want times sigma over square root of n, right? Assuming some value for sigma. And the important thing to note about this is that as n gets bigger, right, the margin of error shrinks down. And this makes sense, right? The more data you sample, the less variation there is going to be in that data, and the more confident you should be about your results. And so, and this all stems from the math we did, from the algebra of linear combinations of random variables, which I've done in a previous video, and I won't belabor those facts. But the point is that that same algebra that shrinks the margin of error as n gets bigger for the mean also shrinks the margin of error for s as n gets big. So as n gets bigger, uh, this wiggle decreases as n gets bigger. So just like uh, just like for means, as n gets large, the margin of error for sigma gets small. Good. Now, so that's the good news. Here's the bad news. The bad news is that what that means is that for every possible n, we need to compute a brand new curve. A curve that encompasses this wiggle. And because the wiggle is different as n changes, the curve changes, then changes. So what we're now dealing with is a family of curves called t-curves. And maybe the best way to think about t-curves is as normal curves with wiggle accounted for. And so the parameters of a t-curve are the same, perhaps, as uh, as for normal curves. You definitely need a mean, and you need a standard deviation, but you need something new, something called the degrees of freedom, which, generally speaking, the degrees of freedom is defined n minus 1. And so what the degrees of freedom tell you is um, which of the many possible t-curves uh, we're going to be using, and that's dependent again on n itself, right? Because n is what determines how much wiggle there is in the standard deviation, and how much wiggle there is in the standard deviation determines how you have to adjust this normal curve so that it makes sense. So, I think less talk, more looking at this thing. Ooh, my recipe that I'm gonna cook later on today. I have to find that again. Hypothesis testing. So, your degrees of freedom, by the way, has to be at least 1, which means that n needs to be 2. You need n to be at least 2 because you need to be able to compute a sample standard deviation, which you can't do with one data point. And let's be real, if you only have one data point, you shouldn't be doing any statistics. And if we're being really honest, you probably shouldn't do any statistics with just two data points either. You really should have, I don't know, 30, like if we're really being real, if it's about something that actually matters, but sometimes it's not realistic, but more than one, right? Anyway, here we have n equals 2, and we can see the shape of the curve, right? I'm going to go ahead and just hit the play button here. And it's going to bounce between 30 and 2. Oh, hold on just a second. See that where it glitched out is when it tried to set n to be 1, and we just talked about how n couldn't be 1. So let's try that again. Right? At n equals 1, it bugs out because it can't make sense of that. So we can see that when n is low, right, it widens out quite a bit. And that's because there's a lot of wiggle in your S. And if there's a lot of wiggle in your S, then you have to account for all that extra wiggle, all that extra potential variability, and it just widens out to be on the safe side in your computations. But as n gets large, it comfortably shrinks back in. And we notice that there's not a lot of visual difference. I'm going to go ahead and pause that. Once n gets large enough, let's go ahead and sketch ourselves a quick little normal curve. Whoops. Yeah. Right, that's the formula for normal curve. And let's go ahead and, I don't like dotted, dashed is better. There we go. All right, and now let's play with this again. Right, we can see now, right, that as n gets larger and larger, and the wiggle gets smaller and smaller. As the wiggle in S goes down, then S is a better and better approximation for sigma, and so your curves do look more and more like the normal curve. In fact, most older textbooks suggest that when n is 30 or more, you don't even need a t-curve. You can go ahead and just use a normal. But this book is written not in the Stone Age, in the modern age, so we are going to go ahead and use t-tests and t-distributions for everything we need going forward. And this is why older books don't do that. Here's a look at a snapshot of what a t-distribution table would look like. And so what we see here is that you have the amount of error in either one tail or two tail, the number of degrees of freedom, which starts at least 1, so n has to be at least 2, and then what those values look like, the corresponding t-scores that go with those areas. Now, imagine, let's go to the distribution table at the end of the book and look at this thing. Oh, it's horrible. All right. So here we have 1 up to 30, and then up to 50, and then skipping values up to 500, which isn't really that unrealistic. So you really only have two options, right? We notice that compared to the z-score table, this thing's much less precise, right? It only gives us like 5 options versus like hundreds, right, of options, or thousands even, for what the areas could be. Here we only have 5. And the reason it only has 5 is because if we wanted to present all 1,000 options, then this thing would be pages and pages and pages wide, right? And then pages and pages and pages long. And that's just unusable. So what most books do is they say, all right, we'll stick to just 30, and then those values are close enough to the z-squared values, uh, so that we don't have to do that. And but that's assuming you're using a piece of paper or a table to do your math, when like there's technology built into everything that will do all the hard computations instantaneously to absurd levels of precision that your paper and pencil math could never match. And so why why bother with that? That extra level of precision is worth it if we want to make scientifically accurate statements about things. So screw the tables. We have technology. It's the 21st century. This is a video on YouTube. Um, I email my class. I don't carve writing into stone tablets and mail it to you guys. So let's forget about that. All right. Otherwise, so let's go back to the question that we posed ourselves, which is about this hypothesis, right? Oh yeah, let's give ourselves an alpha so that this becomes an answerable question. Let's stick with a standard 0.05. Okay, and we stick ourselves a standard alpha, then we can go ahead and answer this hypothesis testing question, right? And it's answered in the exact same way we've done all of these, right? We assume the null, we compute a p-value based on the standard error. It's just the only difference is that our curve is going to be a little bit wider to account for s not being exactly sigma. That's the only difference. Everything else is exactly the same. So we want to do something like that. And our n is 40, and we have our sample mean was 125, sample deviation 20. And we're going to compare that to 110. We have an alpha of 5. We want the probability that, or we want to compute this p-value, and what it looks like is that a 125 is pretty far out there relative to this distribution. And so our p-value is 1.4 times 10 to the negative fifth, which means 0.0000014, and that's definitely less than 5%. So congratulations, we can definitely say purple microelephants weigh more than 110 pounds on average, or not definitely, but as close to definite as you can ever reasonably expect. And then to look at how we would deal with a two-variable problem, it's also the same. So let's go ahead and split this up into purple and blue microelephants again. So let's say purple microelephants had, let's say we weighed 40 of these guys, and their average weight was 125, and their sample standard deviation was 20. And let's say we went and weighed a bunch of blue microelephants. Let's say we could only get our hands on 25 of these guys, and there's I used blue before. I want to change it up. Let's go with green microelephants. So let's say we weigh a bunch of green microelephants, and we only managed to get our hands on 20 of them. And let's say the average sample of this sample was 115, and their deviation was 18 pounds, their sample deviation. All right, what we the only difference between again t curves and normal curves is that all the normal curves are the same, And so it didn't matter what the ends were except to compute the standard error. We compute the standard error in the same way we did in chapter 4, but the question is which t-curve do we use? Uh, and so in a two-variable problem, degrees of freedom is going to be the smaller of the two sample sizes minus 1. Right? And this is just so that, like, if I were to just look at the purple on their own, there'll be some wiggle, right, in the S. If I were to look at the green elephants on their own, there's some wiggle in the S. The one with the smaller sample will have the more wiggle, and so we're going to err on the side of caution, just assume the smaller of the two values. And so let's go ahead and state no on alternative hypothesis. So alternative, let's say mu1 minus mu2 is not 0. The null is that mu1 minus mu2 could be 0, and let's go ahead alpha 0.05. And let's see what we would do here. And it turns out, of course, we do almost nothing differently, right? We would have to find our hypothesis testing app for two variables, and we go ahead and say, all right, for the first sample, we have 40 elephants. When we weighed these 40 elephants, they weighed 125 pounds on average with deviation 20. The second batch of elephants, there are only 20 of these guys. They weighed 115 pounds on average. With a standard deviation of 18, and some comparing to 0 with an alpha of 0.05. I don't want that they're not equal to each other. And here then we see this area, right? This area here plus this area here gives us a p-value of 0.065, which is more than a 5%. So what this means, the way we want to think about this is, if we assume that the purple and green microelephants weighed the same, and we reached into the two populations and pulled out these two groups of data, there's about a 6.56% chance that something like that will happen, which is high enough that we can't rule out the possibility that they really could weigh the same. So here we have to accept the null hypothesis. So hopefully that's helpful. We will talk about differences of scores in the next video.